Hey there, can anyone hear me?
Yes, we hear you.
Okay. Should we get started? Thank you for having me. Basically gonna run through a presentation and talk to it here. You let me know if there's any problems because I have some videos in there. I'm not sure how they're gonna play over WebEx here, but otherwise we're basically I'm just gonna talk to them if they don't show really well. But hey, I'm Danny Lange from Unity Technologies, where I'm leading the efforts in AI and machine learning. And before joining Unity, I want to give you some context here where I'm coming from, because I've done a number of different things. Most recently, I was head of machine learning at Uber. And Uber is an extremely machine learning-centric company. Almost everything is driven by machine learning. There are three key divisions. They're all relying on machine learning. I served all three of them. Number one is the core business, which is basically drivers, riders, and trips. So it's everything that you normally consider related to the Uber app. There's lots of machine learning in there, going from the ETA offered up to prediction of which destinations you're likely to take, etc. A lot of machine learning in the back end, running that business, keeping drivers busy, etc. The second division in there is the mapping unit. Uber is building their own maps. It's a pretty big deal, a very big effort, and they do so from a lot of various data sources. A lot of them are street side imagery. So basically being able to read street signs, business signs, speed limits, all that stuff, and use that information to basically generate maps without doing it the classical way, which is to have 10,000 of contractors sitting and doing that by hand. A lot of automation there. And the last bit is, of course, the exciting thing of self-driving cars in Pittsburgh, and did get a chance to supply infrastructure and help those guys with machine learning. Very interesting space too. A lot of deep learning there, but also a lot of traditional machine learning. Before joining Uber, I was GM of machine learning at Amazon. I ran what's called the Elastic Machine Learning team, which supported over 100 teams across Amazon, to basically get machine learning into every possible team in the organization without that team necessarily being specialists in machine learning themselves. That system was so successful that we decided to make a public version of it and launched that on Amazon Web Services under the brand of Amazon Machine Learning, to basically make any customer of AWS getting access to this. Before that, I was many years at Microsoft doing machine learning. At Microsoft, I had this extreme fortunate moment to get into deep learning very, very early on in 2011 or 12, and work on GPUs from almost from the very beginning. So that was a very, very interesting time. And before that, I did 8 years of startups, 2 startups trying to create a voice-enabled virtual assistant. First 4 years in one company called General Magic, where we built a service for General Motors under the OnStar brand, and then secondly in my own company doing this for Mercedes-Benz, Volvo, Porsche, and a few others. And before that, I was at IBM Research building something called autonomous agents. So lots of different stuff, but always sort of going in a certain direction of creating smarter and smarter systems. So let's take a step back to Unity Technologies. Very few people know about Unity, so I'm always happy when someone walks up and say that they do know Unity, but I don't really expect that. But if you think about games like Pokemon Go and Super Mario from Nintendo, they are all built on our platform. Our software was downloaded 16 billion times in 2016. It's running on 2.6 billion unique devices, and we have over 700 million monthly active gamers playing games written on Unity. Right now, we are a little over 38% of the market share for mobile games, about 50% for console, 70 to 80% of all VR and AR. So we're actually, without anyone really knowing it, the leading gaming platform in the world. And I'm saying platform because we are really enabling game developers to easily develop the games towards currently 30 different gaming platforms, going from iOS and Android all the way over to all the leading VR providers. So you see a bunch of platforms here. We also enable developers to get to easily create games through our asset store, where developers basically can sell components to other developers. So on this slide here, you can see you can get a medieval village for only, well, how much is $50 for the medieval village, and now you can build your game. You have a complete 3D model that you can navigate through down the streets, and you can put your own characters in there. You can maybe buy characters in the asset store, put them in there. Yeah? And looking at this is where I want you to sort of get the first sense of how this is interesting from an AI perspective, yeah? Because you kind of create a virtual environment here, and you can populate it, and that's really asking for some interesting work utilizing machine learning or AI. I want to see how this video comes over. And you need to let me know if it comes over at all. But this is a video done with the Unity engine, and I want you to understand that while this is sort of almost Pixar quality, it is actually real-time rendering. You can download this on a computer and run it. So everything you see here are 3D models that are animated. I'm just going to let it play for a brief moment here. So when the camera is moving around here, we actually have camera tools, yeah. So the 3D model is playing and rendering in real time, and you can just move the camera around like you're the photographer or the director. Okay, so this section here I showed you, it's several minutes long. It's actually an executable. You can download it, several gigabytes, but it will run 30 frames per second on a computer with a high-end NVIDIA board. Yeah, and within what we offered with that package is all the character packs, which is all levels of details for these characters. So a developer could go out and now animate these characters in another setting. We provide an interior pack, an exterior pack. Yeah. So why this is relevant in a conversation about machine learning is that you can imagine that the behavior of these characters, which is rendered in real time, could be interactively controlled through say, reinforcement learning or other approaches, so that you could actually, in a game, in real time, interact with a character that has a very, very, cinematographic quality appearance. So just to give you an idea of how far this stuff can go, and you can imagine that you have VR goggles on, so you could walk around these characters. You could maybe even, poke them and touch them. I wouldn't know if I would dare to do that, and see what happens. Yeah. So that's just an idea of what's right on the horizon. And really, when you look at it, the weakness in the link of all this is actually the storyline, how to implement that. And that's where we really need to take a step back and see how machine learning can help creating more interactive environments. So since you clearly see from my background that I'm not coming out of either the gaming industry or the movie industry, but from enterprise, I want to take a step back and just look a bit like at sort of how most companies, most organizations, they create software today, whether that is for banking, finance, HR, or even gaming. Yeah, it is that they really employ this all-knowing programmer who works with a project manager, a product manager, a program manager, whatever they're called, that sort of really, really spec out every detail of what's going to be built. Program it, run the program that takes, some input, produce some output, and then when they don't get exactly what they expected, they go back and they modify the program. Yeah, and I think of that as an extreme Newtonian thinking back to 17th century, where there's this belief that we can compute everything past, present, and future. And we now know that's actually not possible. Yeah, so it's a unbelievable naive way of thinking of the world that we can write, thousands or millions lines of code that runs deterministically and deal with all kinds of input situations and just always do the right thing. Yeah, and when we see it not doing the right thing, we call it a bug and we go back and fix it. Yeah, but there's really another way. And increasingly we see companies, Amazon is totally into this. Amazon Jeff Bezos, he is a convert. Yeah, he knows that you cannot code your way out of creating a big business. Yeah, what you have to do is you have to rely on learners that rely on historic data that basically build models. You feed new data into the models and you make predictions. Yeah, this is all about distributions of probabilities. We are going, a huge leap forward. We're going from Newton to Heisenberg instead. We know that the world around us is based fundamentally on distributions of probabilities, and if you look at companies like Uber and Amazon, it's all about likelihood that a customer is going to do something. They may do it. They're likely to do it. They may not do it. And basically, you cannot deterministically create an organization that serves the customer efficiently if you think you can do that through a carefully curated set of if and else statements that basically just make all these, rigid assumptions about what customers are going to like and not like. Yeah? And take this even further in deciding what products to sell, what prices to sell at. All that stuff is really stuff that has to be learned. And that's what I'm gonna go a bit deeper into now. Because a lot of companies now think they're into machine learning and they deploy machine learning in sort of under the hat of either data science or predictive analytics or even predictive applications. But then they're also kind of missing the bigger point, which is that it's not just a matter of making that, what I would call, ideal or perfect recommendation. Yeah, it's also understanding. Oh, I went a little too fast here. It's also an understanding the dynamics. So I want to direct your attention to John Boyd, who worked for the U.S. Air Force, and he analyzed air combat during the Korean War, and he basically built sort of a model of how pilots they operated in space. Basically, they observe the enemy, they orient themselves in a 3D position in that space with one or more enemies out there, and then they decide to do something and they act upon it. And what he found was that it's not really a matter of the perfect observation leading to the perfect decision that makes you win a battle in the air. What he found was that it really matters about the speed by which you move through the loop. So his idea was that if you move faster than your enemy, even if you make a mistake, you have time to fix that mistake if you iterate through your loop faster than your enemy. Yeah? So if you, as an example, iterate, at least 2.1 times faster than your enemy. Yeah. If you make a mistake, you have a second loop around to act upon it before your opponent has acted. Yeah. So this is actually super important in many contexts, whether that is business or game development, that you understand that it's not just about making a prediction and then say, the job is done. We already talked a bit about Heisenberg. We all remember him from school. And basically what he says is that there's a limit to our ability to observe reality with precision. Yeah, so that's the observation part. Yeah, you should observe this loop is actually applied every day in good software engineering practices. This is really a representation of the agile software development as well. That in the old days, this loop at Microsoft, this loop will be a 2-year effort in the Office division. Yeah? They would observe for 6 months, orient themselves for 3 months, decide for another 6 months, and they would implement and ship. Done. Yeah. But that's not the way we develop software any longer, especially not in a cloud context with continuous deployments. Yeah. So let's not observe ourselves, to death. Let's observe a little, and then let's orient ourselves and move on from there. It also brings us on to Gödel and his incompleteness theorem, which is basically that when we do these observations, we orient ourselves and we decide to do something. So we build these models. These models will always only represent a subset of truth. Yeah, so they have to be continuously refined. They're never done. Yeah, and sort of the last aspect of this is Boltzmann, which we all know if we drop glass on the floor and it splinters, it does not randomly accidentally come perfectly back together again. Yeah, that's unlikely to happen. Yeah, so some people know this as Murphy's Law too. So basically, when we try to build something, things tend to want to break or change. So we have to constantly loop to maintain things. Yeah. So it's very important to think of this loop in a machine learning context. And I can give examples around recommendation that we're going to get back to later, that it's not just a matter of making a prediction and then move on from there. I want to talk a bit about multi-arm bandit and reinforcement learning, because to me this is like a very important way to implement the OODA loop in applications, whether that is you're selling books, driving taxis, or playing games. Yeah. So let's go to Vegas for a moment. And this is, by the way, one of the most important algorithms at Amazon. Yeah. Netflix as well. This is a very, very important algorithm. Yeah, you want to go to Vegas, and in my childhood, I when we went to the amusement park, we knew that these slot machines, some of them would be better than others. We figured that out as kids. Yeah. I hope that's still the case in Vegas, even though they're run by computers. I hope they're not too perfect. But we would always identify machines that would output more money than other machines. Yeah. So essentially, there are different rewards from these machines, and the task you have is to basically not the task, the objective you have is to maximize your winnings. Yeah. So you play these machines, and you learn something from playing the first machine. You play the second machine. You gain some knowledge, yeah, and you constantly try to compute which machine is providing you with the greatest likelihood of a payout. Yeah. The tricky thing here is that, and we did that as kids. Yeah, we would find that machine that we felt gave us the highest payout, and then we would exploit that machine. Yeah. The problem is that we as humans we are very emotional. So the bandit algorithms help us be automating this process by basically constantly find the balance between exploitation and exploration. So exploitation is that we see one machine paying out more than the others. So we tend to lean towards that machine, but we have some percentage of what our activities needs to go to exploration, where we keep looking for other machines because there may be another machine that provides a better payout. Yeah, and that algorithm or that approach is just absolutely crucial. And I want to use an example at selling books at Amazon. Yeah. So early on, the idea was that I'm really going to personalize the service. So I'm really gonna sell you the books that I'm so convinced that you're so unbelievably interested in, and I'm gonna just push more and more of those books towards you. Yeah. The problem with that approach is that it makes this assumption that you are actually sort of in a closed world, that there's nothing else that will ever interest you in this world. Yeah. And there's nothing to find or explore, uncover. Yeah. So what we found at Amazon is that it's very important to add a component of exploration in there. So when we would show you a lot of products that we would be very, very, confident in that you appreciate, we will also constantly explore other products and show you other products to really probe. And that probing is so important because that's where you're going to uncover what you do not yet know about that customer. Yeah. Finance guys are somewhat actually used to these concepts. They use other terms. In their world, the exploration is more risk. Yeah. So if you raise your risk tolerance, that means that you explore more into unknown territory in your investments. Yeah, that's another example. So multi-arm bandit is absolutely something that is really, really important. I want to take that a step further and talk a bit about reinforcement learning, which is, let's just say, is multi-arm bandit on steroids. And essentially what we do there is that with reinforcement learning, we basically define a number of actions that can be taken. And again, it can be let's take Netflix, the matrix that shows up when you go to Netflix on your TV, on your computer. They can show you different images of movies. They can actually show you different images for the same movie. They actually do that. They have multiple images in their in their repository for each movie or TV show. Yeah, and the rewards function for them has actually changed over the years. Early on, it was a lot about getting you to watch the movies that you already like. Nowadays, it changed. So Netflix nowadays is really just get you to click on the shows they make. That's all that matters for them. Yeah. So they have become way more of a TV station or a cable provider, and they want you to zap between shows. They don't want to tell you much about them. What they really have as a rewards function in their system is the click. If you saw very recently, they now have a thumbs up and thumbs down on movies. The stars are gone. Yeah, so their rewards function is click, and the actions are: let me show you a different set of images for each show, until we detect a pattern that gets you to click. So companies like Netflix, like Amazon, they can really learn what makes you click. And that's the actions with the rewards function. And I want to talk a bit about that. We're going to show some examples. This is a game of a chicken, and basically the actions here for the chicken is basically you can move forward, backwards, to the sides, and you can pick up these. If you pick up these pink boxes, you get a reward, and every time you move, you get a tiny negative reward. You get a positive if you pick up a box, and if you get hit by a car, that's kind of a big negative. Yeah. So look, after 1 hour of training, so it knows nothing about the game. Yeah, it just knows that it can move, and it can either get rewarded or punished. Yeah. So this is very much like training a dog. Yeah. You say every time it does something good, you say that's good, and every time it says something or it does something negative, you say that's bad. And after an hour of training on a NVIDIA GPU using a deep reinforcement learning algorithm here, it is doing somewhat okay. But look, after 12 hours here, it's doing pretty well. Look, getting through the complex of cars here. I could now change the reward function to maybe get more exciting behavior. I could tell it you can never leave one of these pink boxes behind. You have to pick up all of them. But the point here is that I never told it what the strategy should be. Yeah. I want to show you another video. I just got it this morning. One of the guys, he sort of made the chicken work a little harder. So look at this chicken. He just put more cars in there. Look how it waits, and then it goes. It's getting really good. It's not perfect. I think, yeah, there it ran into a car. Yeah, but look how fast it can move. And to me, the fascinating thing here is that I did not hire a C++ or C developer to sit down and figure all this out. Yeah. I basically just let the chicken here try over and over and over. And this is super relevant outside the gaming space as well. Yeah, this is just a demo. Yeah, you actually want to play that chicken yourself. Yeah, it's not fun watching the computer playing so well. Yeah, but the point is, think about you being an Amazon or an Uber or a Netflix or an Airbnb or any one of these companies with a lot of customers. Yeah, you kind of want to be the computer chicken here, learning how to sell more to these customers. Yeah, how to get more clicks to your Netflix original show. Yeah? You don't actually necessarily want to know, how to execute that. You really want to put a big computer in there with a deep reinforcement learning algorithm, and then you want it to learn how to get people to click. just like you get the chicken to cross the road. And it will learn, and we'll talk a bit about that in a moment, even very complex strategies. Yeah, I want to bring you over into the real world and show you a mechanical snake. This is work done by, among other people, Jeff Snyder, who I worked with at Uber on the self-driving car project. Yeah. This snake is reinforcement learning again. This snake knows nothing about how to crawl. It's not coded by a robotics developer. Yeah. So it's using reinforcement learning just like the chicken. Yeah. And did you see it could not figure out? It never figured out how to cross the tall barrier. But then when we made the barrier 2 inches or 1 inch or whatever it is, it can figure out initially sort of randomly. It figures out how to get over by wiggling enough, and then you raise the barrier, yeah, and it reuses what it already learned to cross a taller barrier, and it refines it, yeah. So now what are we now? We're in 3rd grade now, yeah. We went through 1st, 2nd, now we're in 3rd grade, yeah, and it's struggling. Look, but it figures it out in a moment, building upon what it already learned. So you see, it tries to repeat the same technique, yeah. Now we're getting up where, initially it couldn't figure out how to get over, yeah. But we're in 4th grade now, yeah. So we use what we learned in the 2 other grades, yeah. And look at the real time here, the speed by which it moves. So you can imagine how long time this project takes, yeah. And you have to sit and watch this thing, and when it gets successfully on the other side, you click with the mouse and give it a positive reward, yeah. So again, here is an example of if you carefully look at this snake and you count the number of small stepper motors in there, and then think about the software you would have to write in C, C++, C#, Java, whatever you want, that control each of these little motors to make that snake climb over that wall. That would be an incredible programming task. This is what people are actually doing with most robots today. They code them by hand. Yeah. But here's an example of a robot that learned to climb this barrier. Yeah. I want to go back into the virtual world and show you. There's a lot of music on this one. I try to ignore it. 7 movements, 7 actions I can do. The reward is that she really would swing. Yeah. Again, it's the same algorithm as I've showed you. It's the deep learning algorithm all the way through. But in this case, look, she learns to swing. There's now a certain pattern to the actions up there. It's not perfect, but it figured out to do the right movements in the right order. $5 on the GPU. And now look at the actions up there. They are much more systematic if you look at it. And the reward's getting bigger and bigger the more she swings. Okay, so this video of the girl on the swing is developed in Unity, uses deep learning to basically train the character to swing. Yeah? So it's not implemented. We utilize, in that one, it's done by a Japanese developer. It's actually not done by my team, done by a Japanese developer. But the point is that you use the physics engine in Unity here. You have gravity, you have friction, you have inertia. You saw the girl's hair being pulled by gravity. And then you basically say, there are these movements that she can do, and I have no idea in which order they should be put together to have her swing. and then you leave it up to the system. So in some cases, this could be an NPC, a non-person character in a game, that you normally would sit down and hand code to have a proper movement. Yeah. I want to show you back. I promised you to get back and talk a bit more about strategy. So here's an example from Google's DeepMind. So we're using the same algorithm, the DeepQ learning algorithm, in these examples. This is the breakout game, and it's kind of another example of how to train a computer to play. In this case, an Atari game. And you will see this is very similar to the chicken I showed you. Yeah. So it's not super good early on. Actually, it's really, really, really bad. Again, it knows nothing. In this example that DeepMind did in these games, it's basically providing the computer a view of the game and the score, and then 16 movements on the joystick as output. Now, after 2 hours, it's getting really good. Anyone who ever played this game they know that there's a certain strategy. This is not a good strategy. You should not play it from the bottom up. You should actually do something much smarter than that. And look what happens after 4 hours of training. The computer find out that there is a strategy in this game, that by investing early on to get up behind on top, you win. You're much more likely to win. Yeah. And or win faster. Yeah. And that's a very, very, very important example. And there are some other examples from the Atari games where the system detected strategies that were unknown to humankind. Yeah, that nobody knew existed. Yeah, this one is a pretty well-known one. But the point is that the system has, because it's a deep net in this case, yeah, it has this ability to remember a long chain of events that leads to a high payout. Yeah, so in a shallow net. And in most traditional machine learning, systems would just stay at the 2-hour level where they would just play straightforward, yeah, and go for the short-term reward. But it's very important that these systems, they find that there is something called long-term value, LTV. That, for instance, if you were Amazon, yeah, I could sell you 2 books for each $5 today. Or I could sort of back off, and then tomorrow I could sell you a $30 book instead. Yeah, that would be that's what salespeople use for strategy. Yeah, they are sometimes patient because they know there will be next week when I have a chance to make you a big sale. Yeah, and that's an example here of behavior that's very, very complex, and that we have previously not been able to learn. But now we see more complex behavior coming into play. I want to mention AlphaGo is a good example. I also want to mention the poker playing, the deep learning algorithm that was used, or the reinforcement algorithm that was used to train a system to play poker. That the poker players responded to that it was really scary because the system was really, really good as the best players at bluffing. And what the system basically is really good at it because it also uses, solid statistics to figure out when to bluff. So it will only bluff when there's enough probability to get a long-term win out of it. Because when you bluff, you may lose. So the system knows that it may lose, but there may be a long-term win, but that long-term win I should only go for if there's a sufficiently probability for that. And it learns that over time, yeah? So that's also very fascinating. I want to go and just summarize this a bit. Some of the things you've seen here is sort of a mixture of stuff in a real world and stuff in a virtual world. It's important to sort of understand that the boundaries, they are sort of becoming a little unclear. The mechanical snake I showed you, I could train that snake in the Unity engine before actually building it. So after I build it, I would have most of it trained. I would probably have to do some adjustment. I would also be able to train a lot of snakes. I can train maybe 1,000 different snakes, different length, different number of sections, different length in the sections. I can every half an hour I can kill off the snakes that just do not seem to be able to learn to climb the barrier, and spawn new snakes based on the most successful ones, etc. And all this exciting stuff is really from my perspective. I have a physics engine. I can do rendering. I have the assets. I don't have to build characters. I can just focus on animating them. I'm using deep learning. I can produce tons of data when I let these games play, and deep reinforcement learning is just incredible powerful in all that. I want to close out with a couple of pictures here. I did work on self-driving cars at Uber, and everybody is so fixated on all these cars driving around. I believe at this point Google have been driving 2 million miles of real roadway. It took them 8 years. I also saw a note the other day that Uber is driving about 20,000 miles combined every week. Yeah? Put that into perspective. In the U.S., there's one traffic fatality per every 100 million miles driven. So if anyone building a self-driving car is going to come out and say, sure, we're at least not worse off than a human driver, yeah? They need to drive statistically, let's just say 1.5 billion miles without killing anyone, yeah? So Google spent 8 years driving 2 million miles, so they really need to ramp it up to get to that, 1.5 billion, yeah? So on this image I show you here is from the Unity engine, and this is basically a view from a vehicle, yeah. But it's all generated, yeah. So the big challenge when you have a self-driving car project is that you have to have thousands of people labeling the videos for you, because you need to have humans identifying all the objects in the view, so that you can train the car not to hit trees and other cars, yeah, and especially pedestrians, yeah. When you generate lifelike animation, and companies like Apple, for instance, have been training on Grand Theft Auto to bootstrap their self-driving car project. When you do that, as you can see on the next picture, the labeling comes for free, yeah. Blue things in this one are cars, green things are trees, sidewalk curbs are red, sidewalks looks like pink or pink, yeah, and houses are yellow, and the sky is black, yeah. And I can now generate, 1 billion miles of roadway scenarios, yeah. I can basically write some code that makes cars drive up and down, and once in a while they stop, once in a while, a kid will jump out in the street, and you need to train for that too, yeah. So that's an example of how you can train in a virtual world and then get into the real, use it in the real world, yeah. Last video. I love this one. I'm just gonna show you Handle if you have not seen it yet. It's a fairly new video from Boston Dynamics. But this is a robot that is encountering a lot of situations that cannot be programmed for. Yeah, you cannot write C code and embed it in a local computer inside there and predict everything that it's gonna deal with. Yeah, and you see it's keeping the balance all the time. So you see a lot of behavior where you can sort of it uses its let's call them arms to help here. It can handle that kind of stuff. Look how it's keeping its balance. You can see sort of the movement. It's just constantly keeping its balance. It can lift things. And this, again, think about it. This device is not hard-coded from end to end. I want to see on this one, notice the wheels, how they're slipping from time to time, so it just really works hard to keep the balance, yeah? Dealing with all these circumstances that I've never seen before. Okay, here we go. So a mixture of virtual reality, games, real reality, and some examples of how machine learning is really changing the game. And everything you see here, you know, I kind of had a theme of robots and games, but whether you sell books, you sell stock, you sell Netflix movies or music or whatever, it's all the same. So now I will stop sharing, I guess, and go back. Okay. Okay. I saw one question. I see one question in the chat. You want me to respond to that? So I see a question, which is what are the main techniques used. So I want to just really follow up on that. So what I showed you here is a lot of proof of concept. One of the key challenges is if you have a company like Amazon, what do they have? They have over 300 million active customers. They have, you know, 1 billion products in their catalog. So one thing you have to be that you really have to take into account is the cost of machine learning. And that's, for instance, why the bandit algorithm is so popular, because it's so unbelievably efficient. Yeah, there's no deep learning, there's no GPUs involved in that, and there are other ways where you can use deep learning to build embeddings or create vector representations of objects, and it's sort of a one-time thing that when you have learned those, you can now go over and use traditional machine learning techniques. Yeah, so for a lot of these companies, if we go into the gaming space, if you have a game and you have 10, if you're very successful, you have maybe 10 or 20 million gamers playing your game. Again, you can't really run, a deep reinforcement learning algorithm in the back end on a GPU for each of them. Yeah, so you need to sort of constantly balance that, and that sort of makes, I would say the devil is in the details when you move from a something that's conceptually possible to how you would implement it in a real world. Yeah. Things like using deep learning for detecting embeddings in things like products and to characterize or profile customers is very efficient. And as I pointed out, you can then transition into normal, say, clustering techniques and other very, very performant approaches. Any other questions?
Hey, Danny, I'm just going to unmute myself. Hi. Thanks for the talk. I just sent over a link. Google just, the research blog just printed out this federated learning. I don't know if you're familiar with it. I'm assuming you are, but it just sounds like this is something that's game changing in terms of, I guess, lowering the cost of machine learning and, at the same time, just getting all these information um, faster, right, with this prediction model while keeping all the training data on the device instead of on the cloud.
Yeah, I think that we have reached a point where there's a very interesting there are multiple very interesting opportunities where it's actually less about the individual algorithm and more about the methods that you apply around training to make it actually work at really large scale. Yeah. So my example of using synthetic data for pre-training a car, brings up sort of the whole idea of transfer training. Yeah, can I train a car driving multiple billions of miles in a virtual environment, and then what does that mean when I bring it out on the real street? Yeah, if I can do that successfully and bring it out, and then we can polish it off, training, a little on a real street, and then it's fine. Then I have saved a lot of money. Yeah. And I have sped up the process a lot because I can do this virtually at extreme scale, yeah. And that's some examples. The snake is another example of where you sort of the snake cannot solve the hard problem immediately, but if you take a much easier problem and then you make it harder and harder, it can actually do something that's 1.5 times harder than the original problem that it could not solve straight away. So what does that mean if you're on Amazon want to sell books? Yeah. Should we sort of figure out how to train a system on selling books one way, and then it gets better and better, and how's that going to work? So the research into methods for training that are sort of somewhat independent of the algorithm itself is to me a very interesting space.
Thank you so much.
Any other questions?
I don't want to see this. I just want to learn more about machine learning, specifically the mathematical side and how to implement all
character.
I couldn't hear any of that. There was a lot of noise.
Sure. I'll just reiterate. If someone's interested in delving a little bit deeper into the technical side of machine learning, what resources would you point towards? Right now I'm taking a few classes by Sebastian Thorne and Andrew Ning. Are there any, I guess, more hands-on resources, and where would you point to?
Yes. I think that is the problem with machine learning is that there's a couple of reasons, a couple of issues or challenges. Yeah. Number one is that it's really very, very, very much applied mathematics. Yeah. And I have a lot of people come to me who wants to get deep into machine learning, and then I ask them, why didn't they study applied mathematics? And they will be like, oh, I was always really bad at it, or I hated it, or whatever. So number one, it's generally a bad idea to sort of pursue machine learning from the theoretical perspective. A lot of people try to do that. but it's not necessarily constructive. Yeah. The other challenge is that it's moving so fast. So a lot of stuff is changing. Yeah. So there's a lot of stuff that I've seen examples of machine learning groups working 10 to 15 years on something, and then someone walks in the door with a new algorithm, new approach, new thinking, and basically outdo 15 years of work. And that literally happens. Yeah. I have like a handful of examples of that. So my recommendation is to move down a path of agile thinking here, which is go and use some of I really recommend something like Keras, which is a framework on top of TensorFlow. I also recommend TensorFlow directly. There's lots of, and it does not have to be deep learning here, but there's a lot of Python experiments, a lot of tutorials, many tutorials, and I really recommend just basically work through some of those tutorials. They will give an incredible sort of hands-on experience of this, so that it's not really as I would say it's still magical, but it's not cryptic any longer when you go through these tutorials and actually build up, test some, on some interesting data and get some results and get a good hands-on feeling of how this works. That's really what I recommend the most. Reading books, sitting in on Stanford lectures, but you should do that too, but that's not how you really get a good sense of it. It's some hands-on work using Jupyter Notebook to, sort of be able to iterate over this is also very good. And there's some awesome, browse the web, search for some of these, machine learning data sets, visualization. There's some very good examples of data sets that where you can sort of visualize your ability to get the algorithm to learn things the right way to get proper classifications. And when you have done this, it's kind of, you get so deep in that you never, it becomes very real, and the world is not quite the same again after you try that.
Thank you.
Any other questions? Okay. Then I really appreciate you having me. I always love to talk about this, and I hope you are at least half as excited as I am about all this stuff and how it's changing anything around us. And I thank for your time.
Thanks, Danny.
Thank you.
Thank you, Danny.
Thank you.